How ocean water turns into drinking water. Stand at the edge of the ocean for a moment, and the whole idea sounds impossible. An endless body of water stretches out in front of you, and almost none of it is safe to drink. It looks like abundance. It feels like abundance. But if you filled a glass straight from the sea, it would do the opposite of quenching your thirst. And yet, in some parts of the world, that same ocean is being turned into drinking water every single day. Not in a survival show way, not with a tiny solar still on a beach, at industrial scale, through pipes, pumps, filters, membranes, chemical controls, monitoring systems, and some very serious engineering, which raises a fascinating question. How does ocean water actually become drinking water? Because somewhere between the crashing waves and the water coming out of a household tap, salt has to be removed, contaminants have to be controlled, the water has to be stabilized, and the whole process has to happen reliably enough for people to depend on it. So in this video, we are following that journey. From the ocean itself to the inside of a desalination plant, through one of the most remarkable water treatment systems humans have built. Because turning seawater into drinking water sounds like science fiction, until you realize it is really infrastructure. The basic problem is easy to understand. Ocean water contains a great deal of dissolved salt, along with other minerals and impurities. Human bodies are not built to handle that level of salinity. So if a coastal city wants to use seawater as a drinking water source, the salt has to be removed and the final water has to meet drinking water standards. That overall process is called desalination. Broadly speaking, desalination systems either use heat to separate water from salt, or they use membranes to separate fresh water from the saltier source. In modern seawater plants, the dominant method is reverse osmosis, often shortened to RO. That is the version most people are really talking about when they talk about large modern desalination plants. But before reverse osmosis happens, the first challenge is simply getting seawater into the plant. That may sound straightforward, but it is one of the most important parts of the story. A plant needs a reliable intake system that can bring in large volumes of seawater while limiting damage to marine life and managing what comes into the treatment process. Depending on the site, water may be taken in through open ocean intakes or through subsurface systems that draw water through sand or other underground pathways before it reaches the plant. Either way, the water arriving at the plant is still raw seawater. It contains salt, yes, but also suspended particles, organic material, and whatever else the ocean happens to carry that day. So the goal at this stage is not to make the water drinkable yet. It is to prepare it for the much more delicate treatment steps that come next. California's desalination guidance emphasizes that seawater intake design matters both for operations and for reducing harm to marine life. That is where pretreatment comes in. Pretreatment is exactly what it sounds like. Cleaning the seawater enough that the main desalination equipment can work properly. Think of it as protecting the heart of the system before the hard part begins. If too many particles, organisms, or scaling minerals reach the membranes, the process becomes less efficient and the equipment can foul or clog more quickly. So, in practical terms, pretreatment may involve screening, filtration, and chemical adjustment. The details vary from plant to plant, but the overall idea stays the same. Make the incoming water cleaner and more stable before asking a membrane system to do precision work under high pressure. This part is easy to overlook because it does not sound as dramatic as turning the ocean into drinking water, but in reality it is one of the reasons large desalination plants work at all. Pretreatment helps membranes operate more efficiently, last longer, and perform more consistently. Then comes the step most people mean when they imagine desalination: reverse osmosis. This is the moment where the system starts to feel almost counterintuitive. In ordinary osmosis, water naturally moves across a membrane from a less concentrated solution toward a more concentrated one. Reverse osmosis does the opposite. By applying very high pressure to the salty water side, the system forces water through a semi-permeable membrane while leaving most salts and many other dissolved substances behind. The easiest way to picture it is this. The membrane is selective. Water molecules can pass through, most dissolved salts cannot. So under pressure, part of the seawater becomes fresh product water, while the rest becomes a more concentrated salty stream. That is the key transformation at the center of the plant. It is not boiling the ocean dry. It is using pressure and membranes to separate fresh water from salt water at scale. And that is also why energy matters so much here. Reverse osmosis requires significant pressure, and generating that pressure takes power. That is one reason desalination is often discussed not just as a water issue, but as an energy issue as well. Now, something important happens here that people do not always think about. If fresh water comes out one side, something saltier comes out the other. That leftover stream is usually called concentrate or brine. It contains the salts and other rejected materials that did not pass through the membrane. In other words, desalination does not destroy the salt. It separates it out. So the process always has a second question attached to it. What do you do with the brine? That answer depends on the plant and the location. But brine management is a major part of desalination infrastructure. In seawater systems, brine is often discharged back to the ocean, but how and where that happens matters a great deal. Regulators focus on how to dilute it quickly and minimize impacts on water quality and marine life, because the discharge is saltier than normal seawater. California's desalination materials specifically highlight brine disposal and intake effects as central environmental issues. So, by this point in the process, the plant has produced fresh water, but the water is not necessarily ready to go straight to your kitchen tap just yet. That is because desalinated water often still needs post-treatment. It may need disinfection, mineral adjustment, pH balancing, and other finishing steps, so it is stable, safe, and suitable for distribution through pipes. Reverse osmosis removes so much that the resulting water can be chemically different from the water utilities are used to distributing, which is why remineralization and disinfection are common parts of the final stage. This part matters more than it sounds. Drinking water is not just about removing what you do not want. It is also about delivering water that behaves properly in the distribution system and meets the standards expected for public supply. DOE materials describe post-treatment for desalinated water as commonly including remineralization and disinfection, and that brings us to the larger point. A desalination plant is not just a filter. It is a whole chain of infrastructure decisions. You need an intake, you need pretreatment, you need high-pressure membrane systems, you need energy, you need brine management, you need post-treatment. And then, after all of that, you still need the pipes, tanks, pumping systems and utility network that can actually move the finished water into everyday life. That is why desalination is so impressive, but also why it is not a magical solution to every water problem. It can provide a drought-resistant source of supply, especially for coastal regions. It can supplement traditional sources when rivers, reservoirs, and imported water are under pressure. But it also comes with trade-offs. High energy use, significant cost, and environmental questions around intake and discharge. That is why desalination is best understood not as a miracle, but as a sophisticated and sometimes expensive tool within a larger water system. Still, the engineering achievement is remarkable. A resource that looks unusable becomes usable. Salt water becomes fresh water. Ocean water, after enough treatment, becomes part of the same hidden network that fills sinks, showers, glasses, and kettles. And like so much hidden infrastructure, the final experience feels simple only because the system behind it is anything but simple. So the next time you stand by the sea, it is worth remembering that the ocean is not only a coastline or a view. In some places, it is also a water source waiting to be transformed. Not easily, not cheaply, not without consequences, but through one of the most technically impressive treatment systems modern cities have built. That is how ocean water turns into drinking water. And the better the system works, the less anyone notices that something almost impossible is happening behind the scenes every single day. If you enjoyed this video, make sure to like and subscribe to Hidden Infrastructure of the World. Also, comment down below what hidden infrastructure you want to see next. See you in the next video.